Hi everyone, Professor Bob Young here. This is College Trigonometry video number 3. And in this video, we're going to study the following objectives. We're going to use right triangles to evaluate trigonometric functions. We're going to find the function values, which we kind of touched on in our first 2 episodes or videos as well, of 30 degrees, 45, and 60 degrees, or they also have them in radians there, pi over 6, pi over 4, pi over 3, and their relationships. We're going to use equal cofunctions of complements, and we're going to do some right triangle trig in this episode. So we're going to use it to do all kinds of things, including solving applied problems. So again, I love teaching trigonometry because it can be used for so many things in real life. All right, so we're going to come back and do some right triangle definitions of trigonometric functions here to start out. And the 3 things we're going to look at here is we've got this angle theta here in right triangle ABC. And notice whenever they label angles, they always use capital letters, and then the sides opposite those angles, they use small letters to designate those. So there is a relationship between this angle and these 3 sides, the first being the sine of theta is the length of the opposite side, so it's opposite the angle, divided by the hypotenuse, so it would be A over C. The cosine would be the length of the adjacent side. So adjacent's like your next door neighbors, your adjacent neighbor. This side is next to the angle divided by the hypotenuse. It would be B over C. And then the tangent would be the opposite over the adjacent, the opposite side, A over B here. And there's a little tricky saying there that a lot of students will use to remember this. And it is the famous Indian chief Sakatoa. Oh, for you Seminole fans out there. Oh, stop it, Young. All right, so what this is sine up here, the sine of theta, opposite over hypotenuse, okay, A over C. Cosine is adjacent over hypotenuse. That would be B over C. All right, and TOA, opposite over adjacent. So that's just a little way to remember them. A little tricky, catchy saying there, Sakatoa, and we'll be seeing that a lot as we progress. So in general, it says the trigonometric functions of theta depend only on the size of angle theta and not necessarily the size of the triangle. And of course, if we know the sine, cosine, and tangent, we know their reciprocal identities because we studied that in our last lesson or video. So remember, the cosecant is the reciprocal of the sine, the secant is the reciprocal of the cosine, and the cotangent is the reciprocal of the tangent. So again, if you can get, sine, cosine, and tangent, you've got these just as easily. Now what we're going to do next is go ahead and evaluate some trigonometric functions here. So refer to this triangle to the right, and it says find the value of the 6 trigonometric functions in the figure. So they give you sides A and B, so we have to find side C, and notice they do that by using the Pythagorean theorem for right triangles. A squared plus B squared is C squared. They put in 3 for A, 4 for B, squared them, got 25. To get C, take the square root and you will get C is 5. So this is really a basic 3, 4, 5 right triangle that many of you have probably seen at one time or another. So let's go ahead and see if we can get the answers here. So the sine of theta would be the opposite side divided by the hypotenuse. So that would be 3/5. The cosine would be the adjacent over the hypotenuse, 4/5. So once again, if you want to come over here on the side and write Sakatoa, you can. All right. And the tangent would be the TOA part would be the opposite over the adjacent side. Or you could use that little trick. Remember that tangent is equal to sine over cosine in our identities. Lots of ways to start getting this as we move forward. And the 5s would cancel out. Sine divided by cosine would give us 3/4. Or you could do it with our new definitions. All right, now if you've got these three, how easy is it, Young, to get the other three? Well, just take the reciprocals here. 5/3, 5/4, and 4/3. So once you get the first three, you've got the reciprocals quite easily. All right, we'll do a few more examples here just to make sure that we've got this again. So I'll give you a few more right triangles here. And notice on this one, we've got a squared plus b squared is c squared. I like to kind of call this horizontal axis x when I do this. So I'm going to say x squared plus 5 squared, that's a bad square there, sorry, equals 7 squared. So x squared, we just got to find this real quick, plus 20, not 5, is 49. Subtract 25 from both sides, so x squared would equal 24. Taking the square root, x will equal the square root of 24. Now be careful here because a lot of students don't simplify their radicals, and you have to be able to do that. So this would simplify into 2 times the square root of 6. So if this is our angle here, we've got opposite, adjacent, hypotenuse, and we can continue here. Now, another thing I wanted to mention, in this section, we're assuming we're in the first quadrant always. Now, a lot of you may say, Young, why isn't this plus or minus 2 times the square root of 6? Whenever you take the square root of something squared, it's a quadratic equation, usually has 2 answers. Well, in this one, we're just going to be in the first quadrant with all of our right triangles. But later on, ladies and gentlemen, those quadrants will change. All right, so let's go ahead and write this one out here. So the sine would be the opposite over the hypotenuse, 5/7. Cosine adjacent over hypotenuse, 2 times the square root of 6 over 7. And the tangent would be this over this, opposite over adjacent, or we could chop the 7s here and put sine over cosine. We would get 5 over 2 times the square root of 6. Now, don't rationalize anything until we do the reciprocals here. All right, so I've mentioned that in other videos. Do not rationalize until we take the reciprocals here, and then we can. Or some professors will take it just like this. All right, now I'll go ahead and rationalize the tangent here on this first example, multiplying by the square root of 6 over 6 here. And that'll give us 5 times the square root of 6 over 12. The square root of 6 times the square root of 6 is 6 times 2. And then same thing for the secant. We have to go ahead and multiply by that square root of 6 over the square root of 6. And we will get 7 times the square root of 6 over 12. All right, now for this next example here, notice theta now is over here. So be careful now because the opposite side is the 12. The hypotenuse is always opposite the right angle. It's always the long side, so you can tell this. So the adjacent side is going to be over here. And I'm going to call this one y here. Whenever I have one that goes up and down, I kind of like to do the x along the horizontal and the y along the vertical. So this would be 12 squared plus y squared equals 15 squared. So 144 plus y squared will give us 225. Subtracting the 144 from both sides, y squared is going to equal 81. Take the square root, y equals 9. So this would actually be the adjacent side here. So be careful now. When we come over here and do sine and cosine and tangent and so forth, the sine would be opposite over hypotenuse would be 12 over 15. And be sure to reduce your fractions where you can. So 3 goes into both of these, so that would be 4/5. The cosine over here would be adjacent over hypotenuse, 9 over 15, which again reduces 3/5. And then if you wanted to use our little sine over cosine trick to get tangents, the 5s would chop here and we would get 4/3. So once you get them all in this, you've got the reciprocal identities over here. So if the sine of theta is 4/5, the cosecant of theta is 5/4, and we can just go down the line for secant and cotangent as well. So you'll get a lot of problems in the homework, both just straight up problems like this and ones with applications we're going to see later, using these 6 definitions of the trigonometric functions. All right, we have a function values for some special angles now. We've talked about this in prior videos and lessons. It says a right triangle with a 45-degree or pi over 4 radian angle is isosceles. That is, the two sides have the equal lengths here. So if both of these angles are congruent, the sides opposite those angles are congruent. And on any isosceles triangle, now this one has ones here, and then you would get the square root of 2 by using the Pythagorean theorem. But remember, these are special ones here. So these two sides will always be the same. And the hypotenuse will always be the square root of 2 times whatever those sides are. So in other words, let's say that this side was 5 and this side was 5, then the hypotenuse would be 5 times the square root of 2, or 8 times the square root of 2, or I think you get the message here. All right, continuing here now, if we've got our 30, 60, 90 right triangles, which we have already looked at as well, the 30-degree or pi over 6 angle or 60 degrees or pi over 3, remember that it says here the measure of the side opposite the 30-degree angle is always half the measure of the hypotenuse. All right, or what I like to do on this one, I like to call the, let's say this is the 30-degree angle here. If this is the small side, then I like to say the hypotenuse is doubled. Okay, and then there's a relationship between this side over here as well. It's always the square root of 3 times the small side on any 30, 60, 90. So the hypotenuse is twice as large. This way you got everything compared to the small side. The hypotenuse is twice as large, and the side in the middle there is the square root of 3 times the small side. So there is a definite relationship here. As noted, when they put the small side as 1, they doubled it, and then they said 1 times the square root of 3 is the square root of 3 there. All right, up to bat next, we've got trigonometric functions and complements. Now it says 2 positive angles are complements, and some of you may remember this from your old high school geometry courses, complementary angles. If the 2 angles add up to 90 degrees, or if we're talking radians, pi over 2 radians. So any pair of trigonometric functions f and g for which f of theta equals g to 90 degrees minus theta or pi over 2 radians minus theta are called cofunction identities. All right, so the value of a trigonometric function theta is equal to the cofunction of the complement of theta. So cofunctions of complementary angles are always equal. So these are what's called the cofunction identities, ladies and gentlemen. Again, this is in the first quadrant here. So we're going to go ahead and look at some examples. So I just went ahead and I picked the sine of 40 degrees, and I said that will equal the cosine of 90 degrees minus 40 degrees. So what we're saying here is that the sine of 40 degrees is really equal to the cosine of 50 degrees. And if you don't believe me, you can get your calculators out, go to degree mode, punch these in. You will get the exact same values, digit per digit, going to infinity. And then the cosine of 20 degrees here is equal to the sine of 90 minus 20 degrees, or the sine of 70 degrees. Cosine 20 equals sine 70. The cotangent of 37 is equal to the tangent of 90 degrees. Oh, I forgot the little degree thingy on my thing there. Minus 37 degrees, so that would be the tangent of 53 degrees. So notice that these add up to be 90 degrees, or they should if I did my math right there on the cofunction identities and so forth. And that's what they're saying in the figure as well. And again, we'll look at some with radians here as well, just to make sure y'all have it. All right, so one more example here is the sine of 46 degrees using the cofunction identities is equal to the cosine of 90 minus 46 degrees, which is the cosine of 44. And then they went ahead and they took the cotangent of pi over 12 and they said, well, that's 90 minus that, or pi over 2 if we're talking radians, minus pi over 12. Got a common denominator. And again, if you want to go to radian mode and check this, you can amaze your friends at parties. You could say the cotangent of pi over 12 radians, get a number, punch in the tangent of 5 pi over 12, and you will be oohing and ahhing, going, oh, same number. Now, young, where do you use this right triangle trigonometry in real life? One example is called the angle of elevation and the angle of depression. So notice it says an angle formed by a horizontal line and the line of sight to an object that is above the horizontal line is called the angle of elevation. So let's say that we're staring here out the window at a plane up here, and this is our line of sight. This angle right in here would be the angle of elevation from the horizontal straight out. Okay, and an angle formed by the horizontal line of the sight to an object that is below the horizontal line. So let's say we're looking out here and we see this car lined up with this plane here. This would be the angle of depression. We're looking down here. And we're going to find there's a relationship between these as well as we progress. All right, so let's do some problems here showing where you can use trig in real life. And the right triangle trig that we've been talking about, the SOHCAHTOA, so to say, and you're going to get a whole bunch of these for practice. And these are kind of nice practice problems to make sure you understand the concepts here. So it says the irregular blue shape in the figure represents a lake here. The distance across the lake A is unknown. So this is one way you can use trig without even getting your feet wet. To find this distance, a surveyor took measurements shown in the figure. What is the distance across the lake? All right, so the surveyor's over here at point A, measuring a 24-degree angle to that point right across the lake here. And then he went ahead and he did use one of those little maybe rolly wheels or whatever and measured a distance here of 750 yards to the right angle there, which makes a nice right triangle. And then if we're given A and we're given 750 yards here, would you go up here on top and go, would that be sine, cosine, or tangent? Well, if you look at the 24 degrees, this is the opposite over the adjacent. That would be the TOA. So they've set up tangent of 24 degrees equals opposite over adjacent here, A over 750. Multiply both sides by 750 here, and that'll give us A equals this. Use your calculator, go in degree mode. 750 times the tangent of 24 degrees. Now make sure you're in degrees and not radians. You don't know how many people on the test will use the wrong mode throughout the course. And you'll get about 333.9 yards if you're punching it in right. So make sure you get that on your calculator. And this concludes video number 3, College Trigonometry.